Hello everyone, this is Rudree Pathak from Department of Pharmaceutical Technology, LG Institute of Pharmacy, Ahmedabad. Today, I welcome you all on the second lecture of Physical Pharmaceutics B.Pharm Semester 3 according to new PCI syllabus. As we all know, because of the current pandemic situation, we are still not able to resume our classes at the campus. So, till that time duration, we have decided that we are going to conduct our online lecture series by YouTube with the help of Pharma Ignite channel. So, I would like to request you all to kindly subscribe the channel so that you do not miss out anything important which is going on in the campus. So let's begin with our second lecture on physical pharmacy states of matter. So in our first lecture of states of matter, we discussed about what are the three basic states of matter, that is a gas, liquid state and a solid state. Now these are the basic things that we already knew about because of our school studies as well. Then we talked in brief about what is a crystalline structure and how does a crystalline structure differ from amorphous form. Again, that was in brief and that was towards the end of the first lecture. Now in today's lecture, we are going to begin from where we left. So we are going to talk about amorphous solids. Now, if you split the term amorphous into two parts, it turns out to be A plus morphous. Now, if you know what does morphous means, it means morphology or shape. So amorphous means it is not going to have any proper shape, and it is because of this particular characteristic it is going to show entirely different properties from what crystalline structure was showing. Because of a proper shape, because of a proper bonding between atoms, ions and molecules, because of strong intermolecular forces between atoms, ions and molecules, which was giving crystalline structure a proper shape, it was having certain properties. Say for example, it was having a fixed melting point. But in case of amorphous solid, because of this disordered arrangement of atoms, ions and molecules, it is not going to show any fixed melting point, or it is going to vary from the solubility issues as well. Now, as we talked about it in our last lecture, I mentioned two terms. One of them was isotropic. And I also told you that I'm going to describe what is isotropic when we are going to talk about this in our next lecture. Now imagine crystalline and amorphous, both of them are having a 3D structure. Now when we are having a 3D structure, we will be having three axes: x-axis, y-axis and z-axis. Now in case of amorphous solids, it is going to show similar properties along all of these three axes when we are observing them microscopically. So take any property, say for example solubility. Now amorphous solids are going to show the same solubility range of a typical amorphous solids across x-axis, y-axis and z-axis. But this case is not true for crystalline structures. They are not going to show the same properties when we are talking about them or when we are observing them across x-axis, y-axis and z-axis. So this is a major point of difference between crystalline solids and amorphous solids. If we talk about certain examples of amorphous solids, then glass and plastic are the classical examples which are not having a fixed shape when we are observing them microscopically. Please do not get confused. We are not talking about the external structure which these substances can acquire. If we are talking about a glass sheet, it is going to have a rectangular shape. But we are talking about the microscopical arrangement of these kind of compounds. And when we observe them at such a range, we will get to know that they are not having any fixed arrangement pattern. And that is the reason we have classified them under the category of amorphous solids. Now, This diagrammatic representation shows a comparative study between a crystalline structure where you can see everything is arranged. If you observe them closely, you can see the dots and they are connected to each other at regular intervals, and not just regular intervals, at regular angles also. So that is what makes them crystalline structure. If we observe glass, then everything is closed and they are in close proximity with each other as compared to the third diagram, and that is gas. They are connected also. In case of gas, the intermolecular forces of attraction are weaker. We know that, right? Now, in case of glass, they are connected, they are bonded, but when we look closely, the distance between these building blocks, that is atoms, ions, and molecules, is not uniform. The angles are also not uniform. So as you can see in the diagram, it is not going to give a proper shape to glass structure. So as a pharmacist, what we should know when we are having two compounds and one of them is crystalline and the other one is amorphous. So far we have kind of pointed out the differences between a crystalline structure and amorphous structure. But what's next? With these differences in our mind, what are we going to do? And what, as a formulation scientist, what as a pharmaceutics person, it matters us the most. Now, because of the random arrangement in case of amorphous of atoms, ions, and molecules or any other building block, it is going to have entire set of different physical properties as compared to crystalline structure. Now, say for example, we are having a compound like novobiocin. You can see on the screen it is written an example, novobiocin. It is an antibiotic. Now, when this antibiotic was discovered, it was discovered in two different forms. One of them was crystalline and the other one was amorphous. Now, imagine you are working in your lab and you are having two varieties of the same molecule, same chemical structure, guys. The structure is not going to change. Which one of these are you going to select or choose? Now, if we talk about the physicochemical properties or if we talk about the pre-formulation studies, that means when we are selecting an API or an excipient, we need to look at the physical and the chemical properties of these substances before choosing them for a formulation. So coming back to the example of novobiocin, if we are having novobiocin and if I want to prepare a tablet out of it, how am I supposed to select whether I want to go for a crystalline structure or amorphous structure? Here comes the story. Now, if the release characteristic or if the dissolution rate of novobiocin is studied for crystalline and amorphous separately, it was observed that the amorphous one was well dissolved, well absorbed, and it showed greater bioavailability when it was released in the body. Now, what do we mean by that? Because of the disordered or irregular arrangement of atoms, ions, and molecules in the structure of novobiocin, what happened? It could entrap more amount of water molecules inside it. And because of this, the release rates or the dissolution rates of amorphous novobiocin was better as compared to the rigid crystalline structure of crystalline novobiocin. So that led the formulation scientist to select amorphous novobiocin as compared to crystalline novobiocin, because ultimately what do we want? We want our tablet, our capsule, our syrup, our suspension should be released in the body, it should be mixed with the blood, and it should reach the target and it should give the action for which it was initially built. Okay, and if it is not giving that in the required time frame, then we are not going to select it, we are going to reject it, right? So that is the reason amorphous novobiocin was selected over crystalline structure, and that led to the formulation scientists to fetch it as compared to crystalline novobiocin for preparation of the final product. Okay, so there are plenty of examples in which a particular compound is existing in more than one forms, that is crystalline as well as amorphous, and the scientists actually check and compare the properties of each of these compounds, and then they select out of these which should be actually included in the formulation. Okay, so moving further, now we are going to talk about polymorphism. Now we talked about crystalline, we talked about amorphous. Polymorphism is in between, and it is one of the toughest fundamental and one of the trickiest fundamental of pharmaceutical industry, because now we are going to talk about those crystalline structures which are not stable, okay, or which are notorious, and they exist in more than one shape. Imagine you're working with a compound initially which was in cubical shape, and when you compressed a tablet out of it, the shape of the API changes to hexagonal. Now, whatever release characteristic, whatever water entrapment, whatever release, whatever mixing with blood you imagined with crystalline structure, cubical structure, it is not going to happen with hexagonal structure, right? Because the arrangement has changed. The distance between atoms, ions, and molecules have changed. The angles of those arrangements have actually changed. So this is when the problem, or we can say the real question, arises when we are dealing with certain compounds who are having more than one shape, poly plus morph, polymorphism. Okay, now these are the compounds who have different stability in different shapes or different states, and they can change from metastable to stable, or unstable to metastable and stable. So they, all the polymorphs will be of a particular compound will be divided or classified into these three categories: unstable, metastable, and stable. After the stable stage, they are not going to change further. Okay, it is the unstable and the metastable which is going to proceed towards the stable form. If we talk about polymorphs of carbon, diamond and graphite, these two are polymorphs of carbon. They are having the same chemical moiety, but they are having different arrangement of this moiety in their structure. So diamond is the metastable form, and eventually it is going to get converted into graphite, which is a stable form. Okay, so let's have a look at the properties which are going to change when the polymorphism actually exists. Different polymorphs are having different physical properties, same chemical properties. All the polymorphs will be having different melting point. The point at which they are going to convert into liquid state, that is going to change. Okay, so melting point is different. Diffraction, I hope you know what is diffraction. When a beam of light falls on a particular structure, it is going to diffract it back. Now that diffraction pattern obviously is going to change because these polymorphs are having different arrangement of atoms, ions, and molecules in their structure. So that is what is going to change. Ultimately, because of this changes in the arrangement of the building blocks, the solubility pattern, now you know the real problem where it arises when we are deciding a API for the formulation, because they are having different solubilities also. And because of the different solubilities, they are having different bioavailability also, and also the absorption pattern. So you can imagine that if a compound is having 5 different polymers, say for example, all of them are going to show different melting point, different solubility, different absorption patterns, different bioavailability. So it is a possibility that only one out of these 5 will be actually active, and other 4 will be inactive, or even can cause disastrous effects. You never know. That depends on the kind of molecule that we are studying. Okay, so the reasons why such a behavior or such a kind of pattern is actually of polymorphism is actually observed, because remember in our first lecture we talked about crystallization and how crystals are actually formed. We talked that initially the solution will be saturated, then you can supersaturate it with the increase in temperature, and then from that supersaturated solution crystals will come out, crystallize out. Okay, now in any of these steps, if one of the listed factors from the slide actually happens, then there are chances that polymorphism will take place. First of all, the type of solvent that we are selecting. If we are preparing copper sulfate crystals from water, if we are dissolving in water if we are saturating in water, super saturating in water, then obviously the behavior is going to change when we are performing that crystallization in a different solvent. Okay, that is obviously going to change. It is not going to remain the same. Okay, then along with copper sulfate, if other impurities are also present inside that beaker from which crystallization is actually taking place, then it is going to affect the crystallization process, or it is going to lead to the generation of polymers. Why? Because if we are having pure copper sulfate, then there will be Cu2 plus, SO4 2 minus. If we are having impurities, then there will be Cu2 plus, impurity, SO4 2 negative, and that is going to give a different crystal. Okay, you get it? Fine. Then the level of supersaturation, how much amount of salt you are actually keeping or adding for crystallization to take place, that is also going to affect the overall polymorphism process. Then temperature, it is very important, because the next slide is going to justify why temperature is so much important for crystallization or polymorphism to take place. We are going to talk in detail about that. Then the attractive forces between cations and anions, which are actually utilized for preparation of crystals, that is also going to affect the overall polymorphism process. So the most widely learned and examined example of pharmaceutical industry for polymorphism, and one of the most important questions of GTO also, is the coca butter example. Now this name is not new for you. You have prepared suppositories in BPharm semester 1. You have learned in detail about these suppositories also in your theory curriculum. Now suppositories are prepared with an API and a base. Okay, now the base that you select determines what kind of suppository will be prepared and where it is going to melt in the body. Okay, so in preparation of coca butter suppositories, what was done, the coca butter is melt in a china dish or porcelain dish at a particular temperature, and then the API is added. I think you prepared boric acid suppositories. Now after addition of boric acid to the molten coca butter, it is mixed well, and then it is transferred to suppository molds, and then it is refrigerated, and then it was checked at what temperature it melts again. It should melt at human body temperature, normal human body temperature. Now during those practicals, you were given an instruction that please don't overheat coca butter, otherwise it is not going to melt back at 37°C. Now why it was told? Because when you heat coca butter in a porcelain dish on a flame at a particular temperature, you need to restore its original and most active structure, and that is beta form and most stable polymorph. If you overheat, then there are chances that that coca butter is going to convert into the unstable forms, and that is alpha, beta prime and gamma. And when the suppositories are prepared from these unstable coca butter, it is not going to melt again at human body temperature where it is inserted. So the basic motive of preparing a suppository, that it should melt at body temperature and release the medicament, that is not going to serve. Okay, so that is happening because when you overheat coca butter, the original structure, the original nuclei is actually disturbed, and it sets it to unstable polymorphs of alpha, beta prime and gamma. Okay, so this is one of the widest explored example as far as polymorphism is concerned. This will be asked in your GTU exam as well. You will be given detailed notes of these as well, so you can refer why and when this is happening, and at what temperature the stable beta gets converted into the unstable 3 forms. Okay, now there are some other examples as well from the pharmaceutical industry and non-pharmaceutical industry. The first example is chloramphenicol palmitate, and this is an example of a very well-known broad spectrum antibiotic, and it is existing in more than 4 polymorphs, and all of them are showing different solubility. So scientists actually select one of these polymorph from which maximum solubility is achieved, and they prepare tablets and capsules out of it. The next example is from preparation of suspension, and that happens with cortisone acetate. Cortisone, I hope you know what is cortisone, and cortisone is actually available in the form of injectables, and it is not soluble in water, and because of that it is prepared in suspension form. Now the suspension form should have stability in terms of preparation of cake or settling down of API at the bottom. Now all the polymorphs of cortisone acetate were tried, and out of them the unstable polymers, or those which are not selected further, actually showed settling down of cortisone acetate at the bottom, and out of them only one is selected right now for preparation of suspension and injectables of this particular product. The next example is carbamazepine. It is a very well-known antidepressant. Okay, and all the polymorphs of carbamazepine is showing different stability when it is stored, or different shelf lives. So out of them, the one which is showing the maximum stability, or the most stable one, is actually prepared for preparation of dosage forms. Now these are just the examples from the books. You can have plenty of such examples in which polymorphism is playing a crucial role. Some of them are even not reported or discovered so far, but they show the state of polymorphism even after preparation of dosage form, or during storage, or during shelf life. I would like to request you all to kindly search for such more polymorphs. It is going to help you out to understand better that what actually changes when the polymorphism changes, or what actually makes a significant role in terms of physical properties of polymorphs. So in today's lecture, if we wrap up what we discussed in brief about crystalline and amorphous structures. We talked about what is polymorphism and how it can pose the problems for pharmaceutical industry. And then we talked about what are the examples of polymorphism from our industry, and the classical example of diamond and graphite, which are the polymorphs of carbon. So that's all for today's session. I would like to thank you all for your patient hearing. And I would like to mention one more thing in these times of COVID. Please stay home, stay safe, and stay sane. It is tough for all of us, but together I think we can win and overcome the toughest situations. And I would like to ask you all to kindly tell us how do you feel about these lectures, and if you have any doubts, you can always come to us and contact us. The reference of these lectures were from Martin. You can actually have an ebook of this particular reference, and also when obviously the college resumes, we are having copies of this particular book as well. Thank you so much, and talk to us if you need anything.